All right, here's 6-3, day one. We're still focused on angles. Specifically, though, what we want to get into here is how do we look at sine, cosine, and tangent values for angles that are not inside of a right triangle, okay? Now, if you, I think it's clear at this point when we were doing sine, cosine, or any trig function, right? We looked at it inside a right triangle, but we were never looking at the right angle, right? It was always one of the other two. But to be in a right triangle, those angles had to be less than 90 degrees. We call that type of angle acute. And if you compare it to this diagram right here, what it means is the angles that we were looking at were always over here in quadrant 1. What we're exploring today is how does it look and how does it go if we have an obtuse angle like you see. Okay, if we were to graph that on to like draw the angle on a coordinate grid, that would put you in quadrant number 2. What if the angle was down in 3 and it was like a 230 degree angle? Those angles have sine, cosine, and tangent values, okay? And this diagram here, these definitions are kind of how we look at it, okay? You think about this point right here that's plotted. That point forms the angle because then we connect that point to the origin. And of course, you've got the terminal side over here. We draw in this angle. That length right there is x. This length is y. And it's like the hypotenuse is r, okay? Now, you'll see here, it's like when you do this, it's kind of like y. Because you see, we're not inside a right triangle, so we don't use the term opposite, adjacent, and hypotenuse. Those three terms are kind of reserved for right triangles. We now have angles that, again, they're going to have trig values. But we don't use, they're not in a right triangle, so we don't use the terms opposite, adjacent, and hypotenuse. We go with x, y, and r. But if you wanted to think about it like y, that vertical side of the triangle that I just drew, that's kind of like what we call opposite, right? X is like adjacent, and r is always like the hypotenuse. All right, so instead of, for this angle sine value, instead of opposite over hypotenuse, notice that sine is y over r, okay? Notice that triangle that I drew in blue. You always connect that triangle to the x-axis, okay? Kind of think of it like a reference angle. Okay, that we're not looking at that angle itself, but we kind of draw it the same way. By the way, we got to keep track of what quadrant we're in. We do that off of sine, like positive or negative. So x and y can change now that we're moving out of quadrant 1. R is a different story, though. R is always greater than 0. Always. Okay? So let's head down here. Sine is 4 over 5, but it also tells me that for this angle, which keep in mind here, I'm looking for two things off this angle. I want its cosine value, and I want its cotangent value. Best thing to do is just to draw a picture of the angle. The sine value is positive. The tangent value is negative. So I could go to this little chart I have with the quadrants and try to figure out, okay, where is sine positive, tangent negative? Where does that happen? Looks like quadrant number 2 is the only place where that's going to be the case. Okay? So now, I put my point right here. Here's my initial side. Here's my terminal, right? This angle right here, that's theta. I don't have its measurement. It's somewhere between 90 and 180 degrees because it's in quadrant 2. I'd guess something in the ballpark of 100 or a little more. But this is where x and y will come in. Y is 4. R is 5. X is missing, yet again. Pythagorean theorem will bail us out. This one's going to work out to pretty nice numbers. Now you do have to be a little bit careful here, because I take the square root of 9. You got to remember, the square root of 9, technically speaking, has two answers, a positive or a negative. A lot of times we ignore the negative because it doesn't really matter. Here it matters a ton. Notice we're in quadrant number 2, so this x value went to the left. X is -3. Okay, but if you went back up and checked here, you'd see, oh, we're in quadrant number 2. Yeah, that cosine value, right, because x is going to factor into that cosine value. It needs to be negative, so any way you look at it, that x value needs to be -3. Once you've got x, y, and r, getting any of the trig functions is just simple substitution, right? Cosine is x over r. It's -3 over 5. Okay, cotangent is x over y, -3 over 4. Let's try another one, but let's get a little bit trickier. Just a little. Okay? Gave you nice numbers on that one. Not that these numbers are going to be terrible, but... So the point -3, -7. All right, so I'm thinking of it this way, that I go 3 over 7 down. Obviously, I'm not doing this on graph paper, so it's not perfectly accurate, but good enough, right? We've seen this before, that when I'm drawing an angle like this, what I'm really concerned of is, did I end up in the right quadrant? I did, right? We're down in 3, right where I want to be. So here's what I know. By the way, it's always good to mark the angle. This whole thing, that's theta. Okay, somewhere between 180 and 270 degrees. Probably like based on where it's at, like 250, 255 maybe, something like that. To get all of 6 of its trig values, we don't have to know what angle it is. All right, so we saw here x is -3, y is -7. We need r. I kind of hid my 7 there, didn't I? Like, put it in camo. There it is. I don't know why. I'm kind of going all in on the red thing. Just felt right. I don't know why. Oh well. Okay, let's get r. We're not going anywhere to get all 6 trig values. We could get some of them with x and y, but any trig value that involves r, we'd be stuck. So -3 squared plus -7 squared. That whole, let's see, left side, that'll go to 9 plus 49. If you look back to the previous slide, we put a note on there, right? With r, r is always positive, okay? We think of r as a distance from 0, right? It's literally, all right, this point that we plotted, how far is that from 0, 0? So it's always positive. All right, we're set. Off and away we go, all 6 When I said this, the numbers weren't as nice, by the way. So, like, we'd actually seen examples before that have, like, the numbers that come out to be, like, all three sides are whole numbers, but you've seen by now in homework assignments, that doesn't happen all that often. So the bad numbers where that, r comes out to be the square root of 58, which is fine, right? You're typically left with one of the sides being a square root. I kind of skipped over simplifying it. You could look for factors of 58 that are perfect squares. You won't find any. You can't make the number underneath the square root any smaller. All right, sine y over r I'll rationalize that. Cosine would be x over r. Or negative 3 square root 58 over 58. Tangent is y over x. Double negative, though, will go positive. Cotangent, that's just tangent flipped. Let's go to secant. You can think about secant one of two ways. You can just go off its definition, right? That it's r over x. Or you could just flip cosine. Negative square root 58 over 3. Cosecant, same deal. It's r over y, or you could just flip sine. Either way, negative square root 58 over 7. Okay? All right, moving on to next slide here. Trying to think if there's anything else I wanted to touch on that side. I don't think I do. I think that's, you get through all 6, right? I mean, big picture, once you have that diagram, things are in pretty good shape, okay? You can easily get all 6 functions. All right, last 2 slides here. We're going to move on a little bit and get into what's called a reference angle. Okay. So every angle has one. It gives you kind of the different examples of what quadrant reference angles could be in. They're always acute, which means they're between 0 and 90 degrees, if you like talking radians. That notation is pronounced theta prime, by the way. It's a notation that is specifically reserved for radians, okay? Always connected to the x-axis, all right? So here, if you're in quadrant number 1, okay, an angle's reference angle is the same thing. It's the exact same angle. If you're in 2, it's not the case anymore. Here would be your reference angle. Now, these can be helpful if you wanted to. You'll see this more on the next slide for calculating them. Each quadrant has got like a slightly little different rule for getting its reference angle. Okay? If you're in quadrant 2, 180 minus your original angle. Quadrant number 3, original angle minus 180. Quadrant number 4, 360 minus your original angle, right? That's the need for the prime. So you know that, are you talking about the actual angle that you graphed, or are you talking about its reference angle, right? Theta versus theta prime is the difference, so we can tell them apart. Now remember, it's acute, so we should always get a positive angle. That's what you don't need to write that in. That's fine. One thing that we're not going to really get into it in the next slide, but I want you to know is like the deal with reference angles is, right? We first saw sine, cosine, and tangent within the context of right triangles, okay? Where a couple things, the angles are always acute and the trig values were always positive, okay? So here's the deal. An angle and its reference angle, they always have the same trig values. The only possible difference would be positive or negative, okay? So it's kind of like we've explored going all the way around a circle and finding sine, cosine, tangent, secant, cosecant, and cotangent values of any angle that we want, right? But the signs can change. We saw that for the first time, that positive and negative, we could get negative trig values, okay? Reference angles are always going to be positive, right? But we can take every single angle and relate it back to an angle from quadrant 1 that's going to have all the same trig values. Again, the only difference might be when you're outside quadrant 1, that sine, cosine, or tangent value might be negative, okay? But that's kind of the deal with the reference angle. All right, let's find a few of them. We'll just graph it and find it. That's all we're after here. Graph it and find it. Here's 167. Pretty straightforward one to get started, right? Here's 167 degrees. Okay? Here's theta prime. That's what I'm looking for, right? It's in quadrant number 2. Okay, now some of you could just do the math in your head and look at that and be like, theta prime is 13 degrees. That's the reference angle for 167. If you want the math behind that, 180 minus 167 is how you would get that's how you get 13 degrees. All right. A 5,238 degree angle. That's a little bit crazy. Okay. Here's the thing. When we're graphing this, don't forget about your coterminal. Okay? Don't forget about your coterminal. So to kind of get back to where you are, you could take that number and you could subtract 360 again and again and again and again and again. Okay? Just keep doing it. Just absolutely keep going for it. Okay? What you'll notice is you would eventually, right, if you wanted to get back to between 0 and 360, from just subtracting 360. Again, now you have to do it many, many times. You don't want a calculator to help you out, but if you did it again and again, you'll get back to 198, which would tell me, all right, 198, here we are, okay. Reference angle is right there, okay. If this were to come up too, right, I didn't put any examples, well, I did here, but I'm going to get rid of this one just because it's not a good example of a negative. I'm going to switch that one. If you had a negative, right, you would want to do the same thing, right? Use the coterminal thing. Get yourself an angle that's between 0 and 360 before you graph it, right? Because remember, if you're talking degrees, adding or subtracting 360, always legal. Same initial side, same terminal side. You're more or less talking about the same angle when it comes to all of its trig values. Okay? They're all going to be identical. So theta prime is sitting in here. We're down in quadrant number 3 on this one. we can take our angle minus 180 and get that our reference angle, which is in red there, is 18 degrees. Okay? That's one that's down in quadrant 3. Okay? A few more here. Same idea though. Let's just graph it and then let's get a reference angle. If you ever get an answer for your reference angle that's not between 0 and 90, take a look again. Something went wrong, right? You've got to get an acute angle. All right, so when I have something that's in radians, right, we're kind of switching gears here. By the way, just so we're clear here, final answer on the first one was right there, 13 degrees. Final answer on the next one was right there, 18 degrees. So here's kind of the approach I like to take. You got 0 radians, right? Going up to the, basically what's 90 degrees, which would be pi over 2. To make this simple, if I'm going to label the quadrants, I go in the denominator that I have, okay? I go in the denominator that I have. So pi over 2, I do 6 pi over 12. Pi is 12 pi over 12, 3 pi over 2, 18 pi over 12. It makes figuring out where I am a lot easier. Okay, because I can tell when I get the same denominator, oh, 5 pi over 12, 5 is less than 6. Well, guess what? Here I am with 5 pi over 12. Quadrant 1 is a very, very simple case. If you have an angle that's in quadrant 1, its reference angle is itself, right? That's what we're doing is if we're in quadrants 2, 3, or 4, right? We're bringing this back to an angle that's in quadrant 1. I'm going to slide this over a bit so I can get the last two. Hopefully I got 167. That's leaving us for a moment. What I want you to do here is 7 pi over 4, okay? 7 pi over 4. These last three are all in radians, by the way. Going to do the same thing, all right, over here in, you know, which what would be pi over 2, right? Trying to figure out where this goes. 2 pi over 4. Four pi over 4. Right? These are still the same values that you've seen as far as like what goes at those points in radians. Okay, I'm rewriting them so they have denominators of 4 instead of 2. 2 pi would be 8 pi over 4. Because now when I go around, I'm looking, it becomes much more simple, right? I'm just looking at the denominators and saying, okay, where does 7 go? Past 2, past 4, past 6. There it is. Theta 7 pi over 4, okay? Of course, theta prime is right in here. To get it, I have to do 2 pi minus my angle, right? No surprise here with the fraction thing that, you know, compared to degrees, working with radians is always a little bit more work because you can have to switch over to a common denominator. You can be, you know, constantly working with fractions. And we'd get pi over 4, okay? Yeah, I'm gonna slide down a little bit more for our last one. Last one, 5 of these was a bunch, but I wanted you to see a lot of kind of different scenarios that would come up, right? Different quadrants, angles, radians. Here's radians, but we're working with radians as a decimal. Sometimes that happens, Okay, here's how I do this. Convert your each kind of quadrant angle to a decimal. Okay, the one that comes to us the easiest, I think, is 180 degrees, right? That's pi. But I want a good comparison. I'm going to call it 3.14. If I divide that by 2, I'll call pi over 2 1.57. Kind of a different way to look at radians. You're like, oh, you get to what we would normally call 90 degrees. Like that's like 1.5 radians. Okay? Now this will do the trick because I can tell 2.72. It's over in quadrant 2, right? It's bigger than 1.57. It's less than 3.14, right? Putting this in quadrant 2, okay? Theta prime is right here. And as always, our rule to get a reference angle in quadrant 2 would be pi minus our angle. Given the angle was given to me as an approximation in radians, I am more than okay with a final answer in radians. That's a decimal approximation. All right, that was a bunch on reference angles, but we'll call it quits there. Day 2, we'll kind of stay with this theme of trig functions of any possible angle. It'll actually lead us to this discussion on something called the unit circle. So that's coming in day 2.